SwayamPrabha. Digital India. Educated India.
Discuss the velocity field due to a specified rate of extension and specified vorticity. So, we have already seen that the fluid velocity can be thought of as a summation of a uniform velocity plus a velocity field associated with an isotropic expansion plus a velocity field associated with deformation without change in volume plus a velocity field associated with a rigid body rotational motion called vorticity. Now, out of these different contributing factors, we will now consider the velocity field associated with a specified rate of extension, that is when the isotropic expansion is specified everywhere, what type of velocity field it will be, or if the vorticity is specified everywhere, what type of velocity field we are likely to get, these two. So, what remains is of course a velocity field which has no expansion, no vorticity. Like say the fluid velocity at any point can be written as a velocity field which give an isotropic expansion, let us denote it by UE, the subscript E is for expansion. A velocity field that gives an isotropic expansion plus a velocity field which gives that rigid body rotational motion or the vorticity which is called UV, plus a velocity which has no expansion, no rotation, but may have deformation without any change in volume. Let us call it this V. Okay. So, these two contributions we would like to now see. UE which has a specified expansion distribution, rate of expansion distribution given everywhere, and UV point on the protein. Whatever we have got till now is based on pure kinematic consideration. Just considering kinematics, we have seen that the velocity field is likely to be this. Of course, simple kinematics or pure kinematics cannot tell us in a particular situation how much will be the expansion or how much will be the vorticity or whether a particular contribution will be there or not there. This cannot be obtained from pure kinematic consideration. That needs a dynamic consideration as well. But right now we are not going into it. We are considering that okay, these are the contribution, that is a total fluid velocity is simply sum of these, and we would like to see one by one what type of velocity field they will be. Whether particular given flow field that part is there or not, at this stage we are not going into that. Of course, further kinematics has given us that if the flow is incompressible, in that case there will be no rate of expansion. That we have already seen, rate of expansion is 0. So, that part will not be there. However, for a general case it will be there. Let us say that we have a velocity field which has rate of expansion specified everywhere, and let us denote it by delta. Rate of expansion is specified everywhere. Rate of expansion, as we know, is divergence of UE is, we call that say delta. Of course, it is function of x, y, z. At each and every point, the rate of expansion is specified. Divergence of P is the rate of expansion that we have seen, dilatation, or the rate of or the vorticity is specified everywhere. Curl of uv, let us call it omega. The vector sign I am not using, but you must remember that these are all vectors, ue, uv. Now, would like to see what are these velocity fields, what type of velocity field we will have, so that the rate of expansion is delta everywhere and vorticity is omega everywhere. First of all, consider that the only the rate of expansion that is specified, but the velocity field is such that the rate of expansion is everywhere delta, but the vorticity is 0 everywhere. Okay. We will consider one at a time, not two together. So, consider first this case. Divergence U is delta, but U is such that it has no vorticity associated with it. Now, it is also a very simple thing in vector mechanics that any vector can be written as sum of one gradient of a scalar plus one curl of a vector. Okay. This is of course a result from general vector algebra or vector calculus, that any vector A can be written as gradient of a scalar, say gradient of a scalar, let us call that scalar to be xi is a scalar, gradient of a scalar plus curl of a vector, we call that vector B. This is a general result, true for any vector, that all vectors can be written as sum of the gradient of a scalar plus curl of another vector. This then gives that if the curl of the vector is 0, if the curl of the vector is 0, then that vector is simply gradient of a scalar. That is, when curl of a vector is 0, as in this case curl of u is 0, this gives that u v is simply a gradient of a scalar. Let us call that scalar phi. With this, now substitute this u e in this first relation. Gradient of phi is delta. Divergence of gradient, you can try by writing this in standard ddx ddy form, and you can see that divergence of gradient will become simply Laplacian of phi. Divergence of gradient is always Laplacian. Laplacian is a second order operator d 2 dx 2 plus d 2 dy 2 plus d 2 dz 2 in 3 dimensional Cartesian space. Okay. In 3 dimensional Cartesian space, Laplacian is d 2 dx 2 plus d 2 dy 2 plus d 2 dz 2. Okay. Anyway, so we now have the velocity field is such that it satisfies this equation, Laplacian of a scalar function phi is delta, and the gradient of that scalar function gives us the velocity field. This type of equation, this is of course a partial differential equation. Okay. If you write this equation completely, this is a partial differential equation. This can also be written in Cartesian system. And remember this delta, that expansion distribution, rate of expansion distribution is function of space and time, though we are not writing explicitly all the time. This type of equation, when the Laplacian of a function is a non-zero function, then that equation is called a Poisson type of equation. So, this is a Poisson type of equation. If delta is 0, then the equation is called Laplace equation. If Laplacian phi equal to 0, then the equation is called Laplace equation. If it is non-zero, then the equation is called Poisson type of equation. Now, this equation has, okay, since this phi we will also use a subscript e, because this phi is associated with this velocity u e. So, we are using one e here. Now, the solution of this equation, are you familiar with the solution of this equation? The solution of this equation is given by phi e, again a function of x and t. If you want, you can write as a function of x, and okay, is minus 1 by 4 pi, sorry 1 by 4 pi delta prime by r dv x prime. However, x prime is nothing but a general point, okay, another point, and r is the distance from the point x to x prime, that is this r is the distance between the 2 points is r. Delta prime is, this delta prime is the value of delta at x prime. Delta prime is value of delta at x prime. This integration is carried out over the entire fluid. This integration is carried out over the entire fluid. the velocity field then can be obtained as u e equal to grad phi e How much will this be? Gradient of 1 by r is simply 1 by r square minus, and since the gradient is a vector, it has a direction which is again in the direction of the r. So, that to denote that direction, it is written as r by r cube. So, 1 r by r will simply give the direction and r square will remain. The integration is carried out over the infinite fluid. Now, look to the integrand only, delta prime r prime by r cube d v x prime. What does it mean then? That this is the velocity distribution due to infinitesimal volume element d v located at x prime. The rate of expansion associated with point x prime is delta prime. So, this velocity field can be thought of as simply the velocity field due to a rate of expansion delta prime at point x prime, but there is no other rate of expansion. If we consider one small finite element, infinitesimal element at x prime, which is given by d v prime volume, then the velocity field due to that rate of expansion delta prime is this quantity 1 by 4 pi into this quantity. So, we can call that as delta u e. And let us write it this way, delta prime d v x prime by r square into r by r 4 pi. Velocity due to now, what is this quantity delta prime d v prime? See, delta prime is rate of expansion, and dV prime is the volume of a small element. So, delta prime dV prime is again a volume, because delta prime is rate of expansion. So, when you multiply by it the volume, then it gives the total volume expansion. So, this much is the volume expansion over that dV prime, meaning that if we consider say a spherical volume, then the rate of expansion within that spherical element is given by this quantity. We can also think that as if there is some sort of source which produces volume within that small element at the rate of delta prime. Something is there which is creating the volume, a volume source, a source of fluid volume. So, if there is a source of fluid volume which has a rate of expansion delta prime and then over the element dV prime, then it will induce a velocity field given by this. Outside that volume element, everywhere then the expansion remains this delta prime. So, when we integrate it, we get the specified volume element. So, this can be thought of as a volume source placed within that volume dV prime, and the complete rate of expansion also can be thought of as sum of infinite number of volume sources located at each and every point with rate of expansion delta prime, and this delta prime dV prime can be called as the strength of that source, strength of that volume source, that is the volume it is increasing. So, we now have got the velocity field associated with a specified rate of expansion. Now, let us see what the velocity field will be if the rate of vorticity is specified, and once again we will consider that the vorticity is specified such that the expansion is 0. The velocity field is such that it has the specified vorticity, but no expansion. So, consider now the specified rate of vorticity, specified vorticity, but no expansion. That is, we have the velocity field such that curl of u v equal to omega, but it has no expansion, that means divergence of u v equal to 0. This then from that basic vector relation, this implies that u v is a field, vector field such that u v is curl of a vector field. U v is a curl of a vector field. Then if we satisfy if we substitute this in this equation, what do we get? Curl of B equal to, you know what is curl of curl? Curl of curl, this is again a vector identity, it is gradient divergence minus divergence gradient, gradient divergence minus divergence gradient. So, it is gradient divergence of B minus divergence gradient of B. The divergence gradient we have already mentioned is simply Laplacian. So, this can also be written as gradient divergence of B minus Laplacian of B. And this is equal to omega. Gradient divergence of B minus Laplacian of B equal to omega. The equation is in this case is not as simple as in the earlier case. In the earlier case, we simply had Laplacian of phi equal to something. In this case, there is there are two terms, even this. To simplify it, just let us assume that B is such that divergence of B is 0. Just assume, and then the equation will be simplified as before. Let us assume and then we have again the same equation. Laplacian of B is minus omega. We have the same equation, and again we can write the solution, another Poisson equation, and the solution is okay. Again integration over the entire fluid or the infinite fluid. However, before we accept this to be a solution of our original problem, we have to see that whether this has really the divergence 0, because that is what we have assumed. With that assumption only we have got this equation. So, this will be solution only if the divergence of it is 0, otherwise not. So, first we must check then whether the divergence of this is 0. So, we need to check now what is divergence of B? This we have made a change of coordinate here, this divergence x, meaning where the derivative are with respect to x, here we have changed it to derivative with respect to x prime, which has given us a negative sign here. Now, we can apply that divergence theorem and change this volume integral into a surface integral. Okay. Change this volume integral into a surface integral. Using divergence theorem, we now have what it will be. The volume integral will become surface integral, where the surface is the surface of that infinite fluid. Yes. This is what is now divergence of B, but we have obtained this solution assuming divergence of B is 0. So, under what condition this can be 0? This is possible that if the fluid at infinity is at rest. If the fluid at infinity is at rest, then this omega dot n will become 0. For an infinite fluid, this is quite possible that we can consider under a given situation that the fluid at infinity will be at rest, and then that omega dot n will be 0 there. But in many situations it may not be so, that the boundary at some of the boundary this omega dot n may not be 0, the fluid may not be at rest at all the boundaries. However, in that case we may again consider that we will expand that boundary and again take it to infinity, and by that we will make it 0. In those cases where we will be able to make it, only then this is the solution, otherwise not. So, wherever this particular integral, that is at the boundaries the fluid is at rest, and what is it, then this condition will be satisfied, and we can consider that this is the solution. If it is not, then if we can extend the boundary and have a boundary where again the fluid is at rest, then also we can take this as a solution. But in those cases where we will not be able to do it, in that case this is not the solution, then of course, the solution is not known, because we have not been able to solve the complete general equation. We have solved a simplified equation which holds only if this equation is 0. So, we can write it that since the solution needs divergence of B v equal to 0, that is the vorticity, normal component of the vorticity at the boundary must be 0. The specified vorticity is such that its normal component is 0 at the boundary, then this will be the acceptable solution. Okay. This will be the solution only when the vorticity distribution is such that it has 0 normal at the boundary of the fluid. Now, assuming that we have the vorticity distribution such that, as we said that this we can obtain in most cases, at least wherever there is an infinite fluid and the fluid at infinity is at rest, this is satisfied. In case we can expand the boundary to infinity, even though the boundary is not infinite, but we can extend it such that again the normal component at that extended boundary is 0, then also this is acceptable, this is a solution, and you will see that most cases we will be able to do it. So, this is then okay, even though not general solution, but in all practical cases this will serve as the solution. Now, if this is the vorticity distribution, then what is the associated velocity field u v that you have to find? U v is curl of v. So, we have 1 by 4 pi curl of omega by r can you evaluate that curl? Eventually, it will be curl of 1 by r. What it is then? U v equal to minus 1 by 4 pi r cross omega by r cube. Once again we can consider an infinitesimal element and write the velocity field associated that with the infinitesimal vorticity distribution, and Once again, here also we can interpret in the similar manner that okay, if this is the vorticity associated with the infinitesimal element, then the velocity that it will produce or induce, whatever you call it, at any other point will be given by this at a distance r, and when you consider the entire vorticity distribution, this will be the integral sum will be the total velocity field. However, there is a difference with the earlier case. It is in the physical nature that at infinitesimal, that source distribution or expansion rate of expansion distribution is physically possible. You can have in a fluid a small region where there is some non-zero expansion distribution or non-zero rate of expansion, everywhere else it is 0, it is possible. But in case of vorticity, it is not possible that an infinitesimal element of volume, there is a some vorticity non-zero vorticity distribution, but everywhere else the vorticity distribution is 0. That is not possible, because such a vorticity distribution will not have a 0 divergence. Such type of vorticity distribution will not have 0 divergence. So, this velocity distribution on its own cannot exist in a fluid. However, its counterpart for the expansion distribution can exist, it is possible. This alone cannot exist, this can exist, the integrated result, that is everywhere there is vorticity distribution such that the divergence of that vorticity field is 0, fine, but this is not possible. However, that does not prevent us from doing that mathematical interpretation. I think you have come across this relation, at least the mathematical relation elsewhere. If we replace this vorticity distribution by current density, is that relation looks familiar to you? Yes, is not it? Or no? No? You have not come across this relation in electromagnetics, where the vorticity is replaced by the current density and the velocity field is replaced by magnetic field. And you used to call that relation Barth-Savart law. Okay. So, mathematically this is what is Barth-Savart law, and eventually they solve this equation only. The same mathematical equation, that same Poisson type of equation, that is what they solved and got that relation. Eventually that relationship between electric current density and magnetic field also has similar relation, and the mathematical solution is same. And following that, sometime we may call it that this is the velocity field induced at a point r distance away due to a vorticity present at that point, or vortex distribution given by omega prime dV. Like we call that, okay, if there is an electric current flowing through a conductor that induces a magnetic field, in same manner it is also called that if there is a vorticity with this vorticity distribution, it will induce a velocity field at that point. Okay. So, now looking to the complete velocity field in a flow, we have already seen that the complete velocity field is sum total of velocity field due to a specified rate of expansion. We have known what is that velocity field, plus a velocity field due to a specified vorticity distribution. We have also known what is that velocity distribution, and remain the third contribution, which then of course has no rate of expansion associated with it, no vorticity associated with it. So, the third contribution, which we initially denoted by, if you look to that first relation that we wrote, u equal to u e plus u v plus b, and we know that u is associated with a specified rate of expansion, a specified vorticity, and that part u e and u v we have already evaluated. What remains is v, and v is such that it is not associated with any expansion, that is divergence of v is 0 and vorticity of this is also 0. So, our next task will be to find this velocity field. However, before we try to solve this problem and see what type of velocity field we are likely to have, we will consider a few special cases of expansion distribution and vorticity distribution. Special cases as an example. We have found the velocity field due to a general distribution of expansion or general distribution of vorticity, but we would now like to have more concrete, more explicit relation for some specific expansion distribution or vorticity distribution. The first one we would like to consider, or perhaps the simplest one, is the expansion distribution is such that at one point there is a non-zero expansion, everywhere else it is 0, which is possible, as you mentioned that in case of expansion it is possible, in case of vorticity it is practically not possible, but in case of expansion that is practically also possible. We can have at one point where the rate of expansion is non-zero and everywhere else it is 0. It is some sort of a singularity distribution. So, it is known as a singularity distribution or singularity in expansion. Okay. Let us look into this way. Think about a small volume element, and let us say again that the rate of expansion within that small volume is delta prime. Now, think that you are shrinking that volume in such a way that the total volume flow rate that remain constant. The total expansion is delta prime dV prime, as you or we will call delta dV. Okay. Forget those primes, delta dV, delta into dV. dV is that volume element and delta is the rate of expansion. So, total volume or total expansion is delta into dV. Now, we shrink the volume dV in such a way that the product delta into dV remain constant. Okay. That is, when we reduce dV by half, simultaneously we increase delta by 2. Proceed this way. So, when dV approaches 0, this delta will then approach infinite. However, the product is still remaining that delta into dV, whatever originally we had. That is what we are going to consider, that at one point the rate of expansion is infinite, everywhere else it is 0. So, rate of expansion is the velocity field obtained is at any point x, the velocity field is, we have already obtained it, what, 1 by 4 pi into you can write let epsilon approaches 0 . And this constant delta dV constant, let us denote it by m. Then we can write u e equal to m by 4 pi and we already said that delta into dV, that is the total expansion. In this case, that total expansion is associated with a single point, okay. And since it is increasing or expanding the volume, we have called it a source of volume, and this m is then, like delta dV is we defined as the strength of the source. In this case, this m becomes the strength of the source. physically you can think that at one point we are increasing the volume by m, just at one point. You can very easily do it by discharging through a say pipe or tube. In a fluid again you can have some discharge by another tube or pipe at the rate of m. So, that is it, that is a point source. In this case it is a point, so it is point source. So, this is the velocity field associated with point source of strength m, and this is the associated potential. Opposite of source is called sink, where the strength is negative. Okay. We will continue further next class.